the mad scientist. He was like the man I wanted to grow up to be. He could like build all these crazy machines, and he knew enough about welding to be super dangerous, and he knew so much about lasers. And so I absorbed as much as I could from him and a couple of other folks on the welding engineering team that I still work with today, actually, at the Handheld Laser Institute. And so super grateful to have those good mentors early on, because you can't just go open a book to learn about lasers, and you also can't go ask the internet anything about lasers either. It's just not out there.
Well, that's what I was saying. Like, because, you know, especially like you think of academia and curriculum and stuff like that, by the time they get the textbook published, that information is 10 years old. You know, so like with handheld.
Welcome back. You know, I don't know what happened.
There's not a lot of information. I mean, you go to YouTube and you can find some people.
Well, I've just abruptly ended. I wonder if somebody reported me for being dangerous.
Or their shop, or, you know, their small fabrication owner, and they're messing around with it, or the companies that are trying to advertise and push to that market. But it's not like actual information as far as like, here's how to set it up, here's how to dial it in, here's the different applications, here's advantages, disadvantages. Like that information.
Chase the sun.
Null and void unless you're getting the user manual from the manufacturer or something.
Right. Well, what's crazy actually is like the manufacturers themselves don't really even know a lot about how to use the technology. So I'll tell you, you know, I started using handheld laser welding back in 2021 at SpaceX. And, I got my first light weld from IPG, and I was talking to them, and I was like, hey guys, like
Thanks, sir. I appreciate it.
What are some best practices? What should I do? And they're like,
for your information, this channel's about welding. It started out being about welding at home and what you can do at home. Things are going to change a little bit because I've taken a new job where I'm doing a lot of traveling, so it might more be about a career path than anything else.
With handheld laser welding, I had my laser lab. We had a bunch of lasers that I deployed out in the production.
Well, I'm not.
But then right next to the laser lab, I had a metallurgical lab that I had built, tensile testing equipment.
Where am I going?
And then a whole bunch of engineers who were hungry to find new ways to do things. And so it really was the perfect storm.
How do I answer that?
I could make welds. I could turn around and test them immediately.
I guess I can explain it. I'm going to Ohio.
I learned a lot. And
I have a project out in Ohio that I have to go to.
Over, you know, a period of about 3 years or so. And I finally
I'll be there for a little bit.
The internet handheld laser. You know, and in their defense, like, there's no good information about.
That's about all the information I can give. Sorry.
Chinese videos, and I'm like,
the stuff that I work on is kind of
and that's like you and me knowing what handheld laser was
sensitive.
But that's what really drove me to.
Well, I appreciate it. Thank you. I'm hoping to. Everywhere I go, I try to make it more of an adventure than just living in a hotel. So,
like, it's amazing to me that nobody has come out and said today, like, hey, here are all of your basic parameters that goes into handheld laser weld. Here's what happens as you tweak each of them, and this is the resultant effect on weld quality in terms of like the visual inspection or mechanical.
Well, right now I'm listening to Arc Junkies podcast, and they're talking about the laser welders. So I'm kind of curious to see what they say.
And that's also what I'm going to be presenting about at FabTech later this year. Is just the basic fundamentals of handheld laser welding.
Oh, nice. Where are you? Are you going to be at a specific manufacturer's booth, or are you going to have your own booth set up, or are you just doing like keynotes and stuff?
This is going to be like a presentation at FabTech. More likely than not.
Okay.
I'll actually go down for FabTech and weld. The last year I hung out a bunch with IPG. You know, I consult directly for IPG. I consult for their resellers. I consult for their customers. I think they're, for the most part, have been leading the charge here in the U.S. for the past few years. I've got a really close relationship with them. But, you know, I do work with a whole bunch of other manufacturers as well, and try to be as agnostic as I can in terms of our laboratory testing and trying to gain knowledge and give it to people. So I was amazed last year at FabTech. It's like everybody and their mom had a laser. So who knows? I'll probably be wandering around looking at all the lasers, and you know, if people want to find me, shoot, come find me, man. Let's talk about lasers. I love talking about lasers.
I'm definitely going to track you down at some point, because like even so, I tried to taper back my schedule for FabTech when I was here in Orlando, and just do a couple things, because usually it's like from the time I get off the airplane until the time I get back on it, it's like go.
Mm-hmm.
You know, podcasts, you know, hanging out in different booths, going to different events and stuff like that, and like. When it came to Orlando, I was like, I just want to dial all that back. So I'm just going to do one podcast per day. And it didn't work out. I had to, you know, I had other appearances and stuff and commitments I made and shit. And I didn't have the time to go. So like I walked right past the light weld booth, and I'm like eyeballing it the whole time. I'm like, you know, like just trying to check it out, get information on it. But it was like just going booth to booth, you know. So I really want to carve out time. That's the one thing I've been wanting to play with for like the past 3 years at FabTech is the handheld lasers, and I've not had a chance to do it.
Well, with any luck, we get you out to the lab way before FabTech, and you can actually get like some detailed hands-on information, and we'll do some testing together.
That'd be awesome. It might be a little tight, hard work in the schedule, but if I get the opportunity, I'd love to do that.
Yeah, let's do it.
Seems like a lot of fun. How difficult is it to learn lasers, like the handheld laser application?
So I think the easy part, you know, people always advertise and say like, hey, handheld laser welding is so easy, anybody can do it. And you know, for a while I wanted to make a video about teaching my grandma how to handheld laser weld. Like, I think that would be really funny. But the fact of the matter is, like, yes, I can teach my grandma how to weld a coupon on a table, but I cannot teach my grandma how to weld production parts for 8 or 10 hours a day. Right? I think the learning curve, like the truth in that statement is the learning curve to become a good handheld laser welder is very short compared to learning how to be
I got a little bit of a drive to go yet.
Being in community college and I'd never welded before in my life, and you know, this guy that I knew
about 4 hours
had been a welder. He was like, dude, don't learn how to MIG weld, just go learn how to TIG weld. So I never welded, period. I'm like,
I gotta go to Ohio for a project.
It took me like a couple weeks to even be like able to lay down a bead, and then you know, a couple months before I was even like mediocre. And you contrast that with handheld laser welding. I've taken guys from, you know, IT or, you know what, a great party trick is to show up somewhere and do some training and like find one of their executives and be like, hey man, you want to make a weld? And you know, they can make a great weld, but what they can't do
I appreciate
is fit something up or fix something when something goes wrong, or you know, weld out of position, or know what a good or a bad weld looks like. So I think a lot of people with arc welding, maybe they have some habits that make them very, very good arc welders that inherently will make you a very bad laser welder that you kind of have to break. People who have no prior welding experience don't have those quote bad habits, and so they can pick it up very quickly, but it takes much longer for them to learn the rest of the side of fabrication. So you know, I think someone could be a pretty decent handheld laser welder in a matter of, you know, a week maybe of welding parts. So the learning curve is shorter, but there's still a lot of things to learn. Now, that I think is the easy side, is how do you manipulate the torch? How do you pull the trigger? How do you make a weld? What is a lot harder, and what a lot of what I do for my customers is developing procedures and tweaking the knobs and making high quality code worthy welds. That I think is where more of the knowledge is lacking, and what makes it harder to just pick it up and run with it.
And that was kind of like the premise of my question, because a lot of people can MIG weld, but they don't know what the knobs and dials and buttons and stuff do. The same thing with TIG welding. Like, they can turn the machine on, they can, you know, set it at a specified amperage, or like even with going back to MIG welding, a lot of times you walk in a shop and the voltage and the wire feed speed, they've got little paint marker tabs on there.
Oh,
and
yeah.
like, that's how the
every fab shop I've ever known.
Okay, you know, like, I'm just going to turn.
All right, I got to pause it for a second.
Right here,
it's funny they say that. So there's a lot more to welding that people know than just turning a machine on and going. Matter of fact, a lot of fab shops that I've inspected, where am I going? What? Oh, okay. Oh, I gotta go this way, I think. Yep, I do. Okay. Whoops-a-daisy. Anyways, a lot of the fab shops that I inspect, I've inspected them, I looked at the machine settings, and sometimes I will ask the welder, now coming from the pipe industry, going into a fab shop that does bridges and big structures, a lot of their welders, I'll be honest with you, I've noticed, oh shit, let's get over. A lot of the welders I noticed don't actually know how to set the machine up for specific settings. They just have little marks as to what procedure, or they have saved settings as to what procedure they need to weld to. So if they have procedure 44, we'll say, they'll have their little cheat sheet. Well, for weld procedure 44, go to save settings 5, and they'll set settings 5, and they'll just, you know, run their tacks or run their beads with the gun, whether it's spray, MIG, pulse, flux core, whatever. And it surprised me. It's coming from the pipe industry. You You don't have that. That's not really possible for, you know, natural gas or petroleum product piping out in the field. Every welder not only knows what their settings are, but they know how their machine runs, and every machine runs differently. For in a fab shop, you know, the machine they use is not their machine. It's a machine shared by all the welders. So they just hit the settings and then go. And then I ask them, hey, what's your wire speed? I don't really know. Look at the machine. And they, all right, how do you not know? And come to find out, a lot of guys that run, if they're at the same station doing the same thing all the time, or similar things all the time, where they're just following the procedure and following the safe settings, they have no idea. It surprised the hell out of me. So to become a better welder in the industry, I believe that it is really important that a welder understands how to set up a machine from scratch. Don't hit a save setting. Set the machine up from scratch, because the welding procedure does not dictate exactly what wire speed it needs or exactly what voltage. They give you a range, and it's a pretty broad range usually, because usually when we write procedures, we want to write them, one, so they're universal for a lot of different joints and fittings. That way we don't have to write 70,000 of them. But also, two, it gives the welder the opportunity to fine-tune the machines to their liking. And most of them didn't do it. They just hit the settings and just went. And, you know, to their credit, most of the times when I look at the welds, they're fine. A couple little things here and there, but for the most part, never an issue. Not really a big issue. But you take them out of the elements, you put them into something, hey, we got a project where we got to do a A-frame structure that's, you know, different thickness material, or the weld procedure is a little different, or we're using different wire or something. You're basically starting from scratch with them. One, you got to retest them. But also, two, they're all messed up on their settings because they don't have them saved. So, as a welder, it's really important to know the settings and be able to set up the machine from scratch and fine-tune the machine to your liking, not just to a preset setting. Where am I going? Okay. So let's get back to this.
But yeah, I mean, you kind of know how to weld, but you don't know how to weld. But like
I just said,
because if you showed somebody, you know, how to do a handheld laser weld, everything's dialed in, the parts are fit up perfect. You got a pile of coupons there all tacked together, perfect fit up, and like a fab tech, and they're just walking people right through. Oh yeah, I made a laser weld. Look, I know how to laser weld now. No, you don't. Like,
right?
Yeah. You made a laser weld.
Yeah, you made a laser. Like, what are the parameters? Because like with, let's use MIG welding or TIG welding. Well, let's use MIG welding because there's a couple more variables. You got wire feed speed, you got voltage, travel speed, work angle, gas composition, contact tip to work distance. You got all these variables that make a huge impact on the quality of that final weld. What do we have to look at when it comes to laser welding? Because I know you've got some sort of wire feed speed in there. You've got kilowatts you have to deal with. I mean, is there any, like, what other parameters do you have to dial in to get a good quality code-worthy weld?
Yeah, so in terms of handheld lasers versus like big automated lasers, I think handheld lasers are still quite simple. So there's only a small number of variables that go into making a good weld. So number one, what's your power? You know, what's your wattage? I think that's pretty equivalent to your amperage if you're TIG welding. Like, how much energy are you actually putting into the weld?
Okay. Yeah.
The next two big ones have to do with what we call wobble. And so the laser, what makes a laser unique is that the laser power, it's an incredibly high amount of power in a very, very small amount of area, right? So that allows us to penetrate deep into the part and fuse really, really deep compared to arc welding. And the way that we do that is by having a very small, what we call spot size. And that is the diameter of your laser beam itself. And that spot size can vary depending on the make and the model of machine that you get, but it's usually somewhere on the order of 50 to 150 microns. It's like the diameter of a human hair, right? So give or take, right? So like as a manual welder, how do you track a seam with a 50 micron spot? It's impossible. It's not going to happen. So what all of these handheld lasers have is what we call a galvo. It's a mirror that rotates back and forth, and that turns that single spot into a line. So you're able to wobble anywhere from, say, 0 to 5 millimeters wide, typically on most of these systems. And so that allows you to hit a joint. It allows you to control your fillet size and dimensions in some ways. But as it wobbles, so we're worried about the wobble width, and we're worried about the wobble frequency. How fast is the beam scanning across your part? So those are like the three main variables you can set on most machines. And then, as you noted, you've got your wire feed speed. The thing that is different about handheld laser welding compared to arc welding is your wire feed speed controls your travel speed. So the wire is actually pushing the torch along and controlling the travel speed. This is what makes handheld laser welding so, quote, easy and repeatable. And as a result, your filler wire diameter directly controls your fillet weld size. Because 1 inch of wire is 1 inch of weld. It's not like you're MIG welding and you can throw down many inches of wire in 1 single inch of weld and build up a large fillet. So if you're using, say, 035 wire, you're going to end up with somewhere around an 035 or an 040 leg length. Now, if I go up to like a 16th inch wire, I could get somewhere around a 50 or 60 thousandths leg fillet. And then I've been experimenting in my shop for the past 6 or 7 months with a TIG rod feeder that bolts onto the gun, and we can run a 1/8 inch rod, and that'll get up to about a 1/8 or just over a 1/8 inch diameter fillet. But anything larger than that,
that's wild.
It would have to be a multi-pass weld. So I think that's one of like the key differentiators between standard arc welding and laser welding. The last critical variable that I would touch on is your focus position and where your focus position is. The laser is not, it's not like a laser pointer or like a sci-fi laser gun where the laser goes on in one straight line forever and ever. The laser beam actually is more of an hourglass. So you've got what we call a focusing lens in the optics, and it causes the beam to converge down to the focal point, and then it diverges again. And so where you put that specific focal position in relation to your part will control how deep you penetrate and the general dynamics of the weld. So understanding where that focus position is a really critical aspect of handheld laser welding.
Gotcha. Now, when you're setting your wire feed speed, is that directly correlated? You said 1 inch of wire is 1 inch of weld. So like if I have a 6 inch part, I set it for like 6 inches per minute?
Yeah, you set it for 6 inches per minute, you'd weld that part in 1 minute. Now, 6 inches a minute is very, very slow for handheld lasers.
Really?
I think this is another one of those places where
I guess that is
people who are selling the equipment and trying to highlight the advantages will tell you, oh, it's 10 times faster than TIG welding. And it's like, okay, let's back up for a second. What human can actually weld at like 40 to 80 inches a minute? A robot can do that in a straight line. A human can do that in a straight line. Okay, so like these guys who are doing demos at Fab Tech, and they're showing you these welds and they're ripping down a straight sheet. Okay, but what happens when I hit a corner, or what happens when I need to weld a tube to another tube? You got to slow down your travel speed. What I find in practice is that a very comfortable travel speed for most people to start handheld laser welding is somewhere on the order of 16 inches a minute.
Wow, that's pretty
if
fast.
You're going around tight corners, say you want to weld, I've welded down to say like a 3/8 inch diameter rod onto a railing, right? And with that, maybe we're running 6 to 8 inches a minute. We slow it down so we can actually manipulate the torch around that tight radius.
Yeah.
Very rarely do I develop a procedure for someone where we're going faster than say 25 inches a minute. So
that's
I think the real sweet spot for handheld lasers is somewhere between 15 and 25 inches a minute, but it all depends on your geometry and the specific application.
Okay.
That's so fast.
Kilowatt have, like, I keep wanting to equate it to MIG, I probably shouldn't, but like, you got wire feed speed, voltage, they've got like your window of opportunity, right? You have to have so much voltage to push that amount of amperage. Wire feed speed actually controls amperage. If you set your wire feed speed at a specific inches per minute, do you have to have a certain amount of kilojoules, or is the kilojoules based on the joint or the material thickness or the configuration?
Yeah, so this is the crazy thing about lasers, is that all of the parameters are completely independent from one another.
Okay.
So
there's no synergy
you can
mode.
set no, there's not. Now, once you understand the process and you can kind of set up some best practices and you know how each of the parameters relates to each other, you can...
So this is why I was talking about earlier about how welders need to know how to set up their machines. He just said that for the laser welders, laser welders that you see on the TikTok, YouTube shorts of them just ripping through. It's a sales tactic. They make it seem like it's so easy, and it sounds like it could be. But he just said that all the parameters are separate from one another. So that means, so you're setting the wattage on a machine, on a laser welder. He said that earlier. You set the wattage. So volts times amps equals watts. That would mean that you have to set the volts and the amps separately, as well as the wire speed, to get a good weld. So you really have to know how to dial this machine in with the travel speed that you're setting it for in order for this to be a good quality weld. If you have any of those, out of sync from each other, you're in trouble. And he just said there's no synergic mode. Synergic mode is a mode on most MIG guns and even tip TIG where all you have to do is tell it the wire speed and the machine figures out the rest, and it's kind of variable. So if you're traveling faster than what you probably should be on a certain wire speed, it'll up the voltage and the amperage, or the voltage for you. On a laser welder, it doesn't, at least not yet. He just said it doesn't have that. So you have to set this up primarily, and you have to keep consistent. Now that wire on the laser welder pushes you along for you. He said that a couple minutes earlier. And, okay. But, where was I? That got me off track. But, anyways, so what he was saying was that basically you have to know how to set the machine up, and that's what separates I'll call it a assembly line welder from a really good independent welder. So know how to manipulate these machines,
kind of tweak them in relation to each other, but like out of the gate, if you're coming and dialing knobs, yeah, you could just do something that's absolutely crazy and is going to end up with a terrible weld. And I think there's a lot more combinations to make really bad welds than there are to make really good welds. Now, I will say most of the high-end manufacturers these days, both American and Chinese, will give you some sort of preset for the machine. So you don't have to be an expert in handheld laser welding to develop a procedure. You can often just reference, whatever chart they'll give you and have a good starting point. That being said, I think a lot of these presets are shrouded in mystery, and nobody will tell you what they actually are. And if you're trying to tweak them or modify them, I think it gets convoluted really fast. If you try to go qualify,
that makes me want to do it
with like percentage changes to presets that might change with a firmware revision to the machine. It's not an easy way to have a reliable document trail of whatever you're doing if it's a qualified weld. And so my recommendation to people is learn what the parameters do and then develop your own procedures for your qualified welds. Like if you're doing stuff that's not qualified, you don't care who cares, use the presets. But if you're trying to qualify things and have documentation and have repeatability and full insight into the process, you really have to understand what's going on and develop those procedures from scratch.
Gotcha.
Wow.
Now, with kilowatts, like how do you determine how many kilowatts? Is that based off of material type and thickness? Or is there some other...
So there's a couple things there. What we're really worried about here is how deep are we penetrating into the part, right? And that's controlled by a number of variables. Number one, the type of material that we're welding.
Yeah, no, I'm not a fast driver.
A lot of, I think the key word here
is
as
fast as I need to go.
reflectivity.
That's about it.
But people often get confused with general reflectivity of like how well your surface is finished versus the actual material property itself. So
I don't need to do 90 miles an hour.
Material would be carbon steel or stainless steel, nickel-based alloys, titanium. From a physics standpoint, the laser light couples very well. They absorb the laser light quite well. Reflective materials would be aluminum or copper, where in the solid form, they're reflecting 98% or more of the laser energy you're putting into them. Once you build a melt pool, you're probably absorbing closer to 25 or 30% of the laser light. But that's one of the big factors is, are we welding a reflective material or not? And then the next factor is, how fast are we traveling and how wide of a weld do we need to make? When we're talking about depth of penetration, your watts are the big deciding factor. The big knob at the top of most of the machines is your power. But you have to keep in mind that your depth of penetration is directly correlated to your travel speed. And with handheld laser, we're not only moving in the direction of the joint, but the beam's also wobbling left and right across the joint. And so the wider you wobble, the faster your beam has to travel at a given frequency. So the wider you wobble, the less you're going to penetrate. And the faster you wobble, the higher your frequency is, the less you're going to penetrate. So kind of have to find this balance between the reflectivity of your material, the power you have available to you, how wide you need to wobble and how fast you need to wobble. Those are going to decide how deep you're going to be able to penetrate into any given material.
And it's going to be different for every type of material that you're dealing with.
Not necessarily. I would say, as a general rule of thumb, stainless steel and carbon steel and nickel-based alloys
very close.
Operate quite similarly one to another. What's interesting is you get into the world, and this is like what we found is that in 5,000 series alloys, you can actually penetrate deeper with a given set of parameters than you could in 6,000 series. And that comes down to the vapor pressure of the keyhole. When we're digging deep into our parts, we're actually vaporizing the material on the surface.
Yeah.
And there's this plasma plume that comes out of the part, and there's an equal and opposite reaction that digs into your part as well. Now, one of the key alloying elements for 5,000 series alloys is magnesium. And magnesium has a very low vaporization temperature. And that's at least my working theory right now as to why we're able to penetrate deeper on a 5,000 series versus a 6,000 series alloy, is because the vapor pressure of the keyhole is much higher.
That's why
that was a dive down into the weeds.
Well, no, I find that super interesting. So
That's fascinating.
Is that why? Because with 6,000 series, you got silicon, it's got a much higher vaporizing temperature that makes it more difficult to penetrate?
Yeah, I mean, I think, not necessarily more difficult to penetrate, but more so that the magnesium I would call is more of like an active element in the penetration.
Then silicon's more like an inert element.
Yeah.
Okay. So the additional manganese or magnesium tends to help you get better penetration.
It does. Yeah.
Now, are you using the same type of wire that we would for standard MIG and TIG welding as far as like, if you're doing carbon steel, you're using like regular 70S6. If you're doing stainless, you're probably 308, 316, and then the aluminums.
Yeah. The same rules apply for all of your like hard alloys, if you will. So stainless, we do a lot of, I think stainless is probably 90% or more of the handheld laser welding market right now. A lot of 304, some 316, you're running 308, 316. Carbon steel, your standard ER70 works.
So the thing is about welding stainless versus any other metal is that when you're welding stainless steel, you want to keep the heat affected zone as small as possible in most cases. That way you don't make the weld any brittle, you don't get a carbide buildup, you don't lose your gas coverage or anything like that. With laser welding, the big benefit of laser welding is that the heat affected zone is much, much smaller. Dude, you're killing me. Get out. Much, much smaller. So when we're welding stainless steel, it's important to keep that heat affected zone small because of I already listed the reasons. So that's the big advantage to laser welding here, which would make sense as to why laser welding is so much more common or so much more effective on stainless and why it's 90% of the laser welding company's market. Because with laser welding, you can keep that heat affected zone substantially smaller. Let's continue that.
Pretty well. One thing I'll note on the stainless steel wires is I see a lot of people recommending to run LSI wire. There's no need for the extra silicon. So just using the standard 308L or 316L wire is totally fine. It becomes, I think, I like to use 1/16 inch diameter wire as my rule of thumb. It gives you a bigger fillet. It's more forgiving in terms of gaps and fit up. And it can be a little tricky to find 1/16 inch carbon steel wire. And so I often, whether you can find S2 or S6, it's kind of just, what can you find in 1/16 inch. And I think the world of stainless steel hand-tool laser welding is pretty well fleshed out. Carbon steel metallurgy is very complex comparatively, and it can be done. I think it's fairly common. I'm very curious on my end to do more investigation and more testing. I've done some stuff for people on high carbon steels and looking at deep penetration groove welds and materials that you would typically have to preheat. And because your energy is so concentrated and your heat affected zone is so small, we can avoid sometimes the formation of your coarse grained heat affected zone, which leads to the formation of martensite and hydrogen-induced cracking. And so we've done some stuff for people where you don't actually have to preheat some of these high carbon steels. But, how does that affect the rest of your weld metallurgy? I think it's going to be a really, really interesting area to go explore here in the near future.
Okay. Now, have you done anything with like cast material? Because you're talking about like preheat, post-heat. I mean, that's one material that's like highly susceptible to preheat, post-heat.
Yeah, I haven't had anybody come to me asking about welding any cast iron yet. I'm sure it will happen. I'll tell you, like with the high carbon steel, it was mostly plate that we were working with, but I myself was pretty surprised at the lack of cracking even without preheat. It was pretty awesome.
Now, is joint geometry like a big consideration? Because I know like with your standard arc welding processes, you can't have a joint, the prep can't be deeper than the width. Otherwise it's prone to cracking that way. Is that the same? Because like I would imagine with laser, you've got a deeper penetration, but a much narrower weld profile. And if you had that in an arc welding process, it'd be prone to cracking at that point. Is that the same with laser?
I think it depends on the application. So what we're talking about here is avoiding what we would typically refer to as solidification cracking. And it's really a function of your chemistry, your weld profile, the residual stress in the part, and your rate of solidification. So I have welded some parts where we've found cracking, depending on how we've tuned the parameters. But this is no different from MIG or TIG welding. You still see the same thing depending on how you TIG weld some of these things. I'll say, stainless steel, as long as you can control the chemistry of your material, it's very resistant to solidification cracking. Nickel-based alloys, I think in some ways might be a little bit more susceptible if you're going after a deep penetration keyhole weld. What's been really interesting has been diving into the world of aluminum handheld laser welding over the past few months. I had probably 6 to 8 customers come to me within a month of each other asking about cracking in aluminum alloys that they were handheld laser welding. And it's not always open to the surface. It's sometimes subsurface that you're only going to see in a macro, or if you do a tensile test, you're going to notice that it's weaker than you expected. And I think part of that is due to the deep penetration of your handheld laser welds. You're bringing more of the parent material into the fusion zone. And so your standard filler materials that have been designed, 50, 60 years ago for TIG welding, the alloying content is designed for very little base metal dilution, and they work very well. But if you go try to use those same materials with handheld laser welding, often you see cracking. And so we did a bunch of testing over the past 2 months, looking at different filler materials and different parent materials and different sets of parameters, and seeing what we could do to optimize chemistry and eliminate solidification cracking. And ultimately we found a solution that works really well. It's unique. I don't think there's anybody else that's doing it. If you're curious about it, let me know.
Yeah, but are you going to say it?
I'm hesitant to say exactly what the secret sauce is right now, just because I think we're on the leading edge, and we've invested a lot of time and money into it.
Don't let the squirrel out of the bag.
The information will come out eventually, right? You can only keep a secret for so long.
I'll ask you afterwards.
Yeah, it all comes down to controlling the chemistry inside the joint.
Okay, I was going to ask if you tried 4943 filler wetter.
So 4943 is one of the more resistant materials. You know what's really interesting? I'll tell you what doesn't work, and then I won't say what does work. How about that?
There you
go. So your typical, let's say you want to go weld some 6061, you're going to pull out your 4043 rod, right?
Typically.
Well, from a typical hardware standpoint with handheld laser welding, you're using a 12-inch spool feeding through usually like a 10-inch whip. And so 4043 kind of feeds like a wet spaghetti noodle. It just bird's nest immediately. So it's really not possible. So a lot of the recommendations from most manufacturers and people that are doing handheld laser welding is, well, hey, just use 5356 because
it's harder.
It's stronger, it's stiffer, it feeds better. You know, it doesn't feed perfectly, but at least it feeds. Yeah, you can make an okay weld with 5356. Don't cut it open. Don't look too close. Just be happy with how it looks on the surface. Okay.
Micro porosity in there.
It's the porosity is not the problem. It's actually the chemical composition of the weld often leads to a solidification crack, and it'll either form in the parent material, where I think there's poor mixing, or it'll form at the root, where again I think there's probably poor mixing and improper dilution of your alloying elements from your filler material. I've actually got a handful of samples at Ohio State right now. One of the professors there is doing some chemical analysis of some cross sections that I sent him to kind of confirm some of these theories about poor mixing. And I'm pretty convinced that a lot of it has to do with the dilution, but I think there's also in some ways what we would call an arc welding in unmixed zone. Now in arc welding, your unmixed zone is typically like a very narrow, thin film along the edge of your fusion boundary where you melt the parent material, but it doesn't necessarily get pulled in and mixed with your filler material. I think we have a much larger unmixed zone depending on how the parameters were developed in some of these aluminum materials, and that's where a lot of your cracking comes from.
Makes sense.
We did try 4943. 4943, I think it feeds through a standard feeder a little less well than 5356. It still feeds, it feeds better than 4043. It's more resistant to cracking, but as soon as you add some sort of restraint, you can bring the cracking back. So let's say you make a T-joint and you weld one side with 4943, probably looks fine. You go and weld the other side, it's likely going to crack.
Wow, deal with stress well.
Right. Yeah. So it's still pulling apart at the very end.
Wow.
So if you find the silver bullet, it's very resistant.
Well, one side with 5356 and then the other side with 4943.
Well, what's crazy is it's really interesting actually, and I think part of it has to do with the stress situation. We've done a number of groove welds with 5356 that we've done bend tests and tensile tests and weld qualification to D1.2 requirements for people, and the groove welds tend to do fine. The issue is typically with the fillet welds, I think, because of the joint geometry and the inherent stress concentrator at the intersection of those two joints.
And most fillet welds are not full penetration, so you leave that opportunity for a crack to fall right at the leading edge of the piece.
If you're looking for a solid, reliable machine without emptying your bank account, you need to check out Everlast Welding. They've got everything you need from make and take machines to multi-purpose units that absolutely hold their own against big names. And here's the deal. When you order any machine that comes with a stock foot pedal, simply type in Arc Junkies in the comment section at checkout, and Everlast is going to hook you up with a free Nova foot pedal and take towards an upgrade. So head on over to everlastwelders.com, check out their lineup, and get dialed in. Everlast Welders. Weld mean, weld green. Big news for welders everywhere. The International Welding Bureau is here. If you're tired of chasing research and dealing with outdated systems, the IWB is changing the game. They're using smart technology and AI to streamline qualifications, connect you with real job opportunities, and make training more affordable. Members get access to a global job board, safety training, pre-approved procedures, and all the resources you need to stay sharp and stay working for a fraction of what you're used to paying. The IWB is all about raising the bar for welders and bringing pride back to the trade. Learn more at internationalweldingbureau.com. Now let's get back to the show. Okay. Now, is base metal preparation and cleanup still like a big factor when it comes to laser, or does it burn off like, because aluminum oxide is like a huge thing, especially when you're TIG welding aluminum. You know, spool guns tend to kind of blow right through it just because it's inherent in the process. But whenever we TIG well, we want to make sure we take off that aluminum oxide, prep it with some acetone or dechlorinated brake cleaner or something to that effect. Is it the same with laser welding, or can you bypass
my recommendation, my normal recommendation to people is treat your joint prep the same way you would treat a TIG weld. For stainless steel, carbon steel, wipe it with acetone. With stainless steel, remove any oil that's on the surface, you're going to be good to go. Carbon steel, you really got to remove any of the oxide that's on there. It'll float to the surface and your weld will look like garbage. It'll weld, right? It'll stick together, but like your weld is going to be ugly. With aluminum, it's incredibly important to properly clean everything and then weld it within a given amount of time before that aluminum oxide has time to reform.
See what altitude we're at, because we've been climbing this hill for a while.
Now, you mentioned like welding a D12 and some of the, some other specs and standards. Is there a code out right now that covers?
Thank you, I appreciate
laser
it.
welding,
I will be
handheld or mechanized or anything like that, or is it still kind of like the textbook where the publishing date's 10 years behind the technology?
Generally speaking, I think the AWS moves very slowly. I am on a number of subcommittees to get it added in. Hopefully we see it come into D17.1 sometime in the next year or so. What's interesting actually is the first code book to accept it as a process was ASME Section 9, Boiler and Pressure Vessel Code, which I think is really awesome. The Canadian Welding Bureau actually came out with a position statement last fall, and they said, hey, look, handheld laser welding is a real thing. We recognize it.
Star Wars.
Close attention, because the other thing that I got to worry about in this part of the state is
here are the steps to take to qualify,
especially up here,
and here are the codes to reference, and here is like the best practice to go do that. Now the CWB operates very differently from the AWS. I've done a lot of work in Canada over the past year, and it's really interesting to see how they work versus how the AWS works. My dream is that the AWS would just come out and say, hey, look, handheld laser welding is a real thing. Here's what you do to qualify weld, and by the way, we accept it to all of our process, like all of our codes. I don't think they're going to do that.
It's kind of a blanket statement, because they're like, here's the processes you can use, and here's the ones that are pre-qualified. All of these are not pre-qualified. Here's your parameters if you have to develop something that's not pre-qualified. So
right.
It's like a general kind of cover your ass of, here's a, pre-qualified, or qualify the procedure. Here's your parameters, but there's nothing in there as far when it comes to lasers. Like you have your tolerances for plus or minus, percentages of gas mix, travel speed, and all that. But there's no kilowatts in there. There's
So what's interesting is like it's not. So it's called out explicitly in D17.1, which is the Aerospace Fusion Welding Code. I think D17.1 is kind of like the magic code. As long as you know how to manipulate it. Well, it's crazy, right? Because you think about aerospace welding, you're like, man, aerospace, it's got to be like very strict and very high quality, and it's all got to be perfect. But
not exactly.
The fact of the matter is D17.1 is very, very strict when it comes to inspection and acceptance criteria, but they're very, very generous when it comes to everything else. And a lot of it comes down to the engineering authority, and can you generate the data to back up your claims and qualify this weld? And so that's part of what I think was like, part of the perfect storm back at SpaceX was we had a lot of leeway with the code. Laser welding generally was already included in D17.1, and so it wasn't too big of a stretch. We could generate all the data that we needed. D1.6, D1.2, D1.1, they don't explicitly call it out. D1.6, D1.2, I think are pretty straightforward to qualify joints to. D1.1, it's also pretty doable. I think the big issue that I run into with customers with
thickness.
D1.1, D1.2 is more when they're doing like structural welds for like buildings that have to be made to state code. Then the hiccup becomes, hey, you need a minimum 1/8 inch fillet weld, and if you can't make that, well, sorry, your weld doesn't pass. And I've got customers who make gates and railings, and what's crazy is you can make a handheld laser weld that has a 50 thousandths leg length that outperforms a TIG weld that has 150 thousandths leg length.
Because I would imagine because of the depth of penetration.
Because of the depth of penetration, but like there's no way in any existing codes, like all the existing codes have been written for arc welding, and all of your design engineers are so familiar with arc welding that that's just what they're speccing. Like the min weld size is 1/8 of an inch period, for some of these things. And sometimes you can get around it, sometimes you can't. I was visiting a customer like a month ago or so and looking at all these big stainless steel parts that they were making, and in my head, they have this like hopper thing that holds some material, right, and travels through a factory, and they've got it's made out of maybe 10-14 gauge, somewhere in between there on the walls, and it's got this big 3/8 inch thick plate welded to the end of it, and they've got these big 3/8 inch fillets. And I'm like talking to them, I'm like, hey, how strong does your weld actually need to be here? Like, I don't think you need a double-sided 3/8 inch fillet weld on this thing. And like in my head, I'm like, okay, well, how much does this weigh, and how much load do I think this needs to react? Because like in my head, I'm like, I know for a fact, like if you watch that video with Nate and we did that tensile testing, that 1.5 inch long weld that had a 50 thousandths leg length reacted 12,000 pounds of force. And so in my head, I'm telling the guys, I'm like, a 50 thousandths laser weld 1 inch long can react 8,000 pounds of force. Like, there's no way you're carrying 8,000 pounds of stuff in here. And by the way, you've probably got like 50 feet of weld on this thing. Like, your weld's way oversized. And I think that's one of those things that is going to take some time for design engineers to understand and manufacturing engineers to understand, is how big their welds actually need to be. This was a really big circular conversation at SpaceX too, when I was trying to convince people to weld the nose cone. I was like, guys, let me do this. Let me reduce distortion, and it's going to be awesome. And they're like, well, your weld has to be as strong as our current MIG weld. And I'm like, well, you guys, I'm like, that's not going to happen, but I can do way less distortion, and I'm pretty sure it's still going to be strong enough. And they're like, well, actually, we don't really know how strong it needs to be. We just know this weld's strong enough, right? And but that's the way people approach things.
Oh, yeah, we've been doing it like this for 20 years.
Oh,
right?
God.
But then a lot of these components too, there's a guy at Lincoln that calls it the moron theory.
Yeah, Charlie Crow.
So that's one thing. I'm going to definitely pause it here. That's one thing to remember in the welding industry too, depending on who you're learning from. There are plenty of people, plenty of welders that been welding for 30, 40 plus years. I've tested some of them, and we'll get them tested on a new procedure or something, and we go to test them, the weld fails, and I'm trying to explain to them why it fails because they don't believe it, and then they come out with the saying, and it's always said like this, I've been welding for 45 years. I've never had a problem. Like, well, you've been welding wrong for 45 years. I don't know what to tell you. It's just is what it is. So be careful with who you're talking to, because you can pick up bad habits. I'm not necessarily saying that, if somebody has a couple bad habits, that means they're going to fail. Like, no, that doesn't mean that. There's bad habits that I've picked up that I know when I was teaching my students. I would tell them, like, hey, don't do this. One of the biggest bad habits is for a TIG welder is breaking the tungsten. So a lot of times to save time, instead of grinding the tip down, if I get it contaminated, I'll break it off and then regrind a tip on it. You really shouldn't do that. One, believe it or not, you can actually bend the tungsten a little bit, but also two, you get micro fractures. And the micro fractures in the tungsten, what'll happen is it'll disrupt the arc going through the tungsten. And when you get an arc to start, the arc will do this wandering thing, and it'll cause all sorts of problems. It could contaminate your tungsten even quicker because you have those microfractures in it that you can't even see with your naked eye. But also, too, it can cause a lot of issues. Between contamination, arc control, being able to grind your tungsten, it's a lot. I mean, splitting your tungsten is even discontinuity kind of by itself. So that thing to watch too. Be careful who you're learning from.
Yeah. So Nate told me about this, and I was like, dude, this is such a great thing. Where it's like you have your design engineer, where if you're lucky, your design engineer knows how strong their weld needs to be. And like in a best case scenario, let's say your design engineer knows it needs to be a 1/8 inch fillet. Well, they want to feel better about it, so they make a 3/16 inch fillet on the drawing, and then you got to the shop floor, and the welder's like, well, I don't want my weld to get rejected by the inspectors. They make a 1/4 inch weld. And like before you know it, you've got this weld that's 2 or 3 times bigger than it ever needed to be.
That was a lot.
That's one of those things that I think is going to take some reprogramming of people to understand how to actually size welds, because historically it's very difficult to make an arc weld that's smaller than 1/8 of an inch without getting some sort of lack of fusion with a MIG weld. Now, with a TIG weld, you could do it. It just takes more and more skill. But it's one of those things that people just need to understand how to do it and how strong the weld is and how to apply it in their given application.
Yeah, I mean, there's a lot goes into it. I mean, and especially with it being a new process, everybody's apprehensive or afraid to approve something or say, yeah, we can do it this way, even though it's going to be better. Like the data's not out there, like we were talking about earlier. Like you're lucky to get some information in the user manual. There's no textbooks written about this stuff. There's no, accurate YouTube videos or Instagram reels that you can refer to. Like, that's why what you guys are doing at the Handheld Laser Institute is like so paramount, because I mean, you're essentially blazing the trail for the rest of the industry.
Yeah, I joke about writing the book. I've got, there's no money to be made in writing a book, but the information's not out there, right? So like, we've got a lot of the data, we've got a lot of the knowledge. I've got the chapters laid out.
So you're writing a book?
Eventually, someday, I think so.
10 years from now.
But yeah, 10 years from now. But like, in the meantime, but let's be real, man. Like, nobody reads books, okay? Yeah. And that's one of those things that like, I don't necessarily like being on camera. I'd much rather like hide somewhere and just do nerdy garbage. But let's be real, in today's world, people don't even have a long enough attention span to listen to this entire podcast or even watch an entire YouTube video. So how do you educate people? I'm going to sound like an old geezer. Unfortunately, I think the way to educate people is through TikTok, right? And so like, how do we put out stuff that is going to be readily available and easy to digest, I think is the trick. So, if I wrote some cool nerdy paper, there's going to be like 10 engineers that read it. Right, but if we make some video about it, as much as I hate being on video and as much more work as it takes to make a video, that's the way to make knowledge.
Put it in. You can get away with 90, like the first 10-15 seconds, it's got to be a real big hook. And that was the funny. It's funny you mentioned that, because like I never watch a YouTube video greater than 30 minutes. Or actually greater than, unless it's something like I'm intent on, like I'll watch blacksmith, videos. Like I'll just hit play and just let it just roll through. Right? I'll watch those. I like watching people perform their craft. And when Nate sent that video, I looked at the time length. I was like, it's 29 minutes. To end, and it didn't seem like a 30-minute video. It was very entertaining, very educational. But yeah, you're right. Like people have the attention span of a goldfish, and that was one of the things when I was younger. I got into like doing magic, like magician type stuff. I'm not into it anymore, but like that. I remember one of the things that the guy, one of the magicians, like a professional magician, told me. He's like, if you want something to remain a secret, publish it. He's like, if you want to come up with a trick, you want it to remain a secret, publish it. Nobody's ever going to read it.
No, but nobody will ever read it.
And I think I was like 12 or 14 when he told me that, and it like still rings true to this day. It's crazy. Like, and the attention span is just getting shorter and shorter and shorter. But I mean, like I said, I think the work that you're doing at your facility is you're literally blazing the trail for everybody else. Because a lot of people are apprehensive because it's new technology. I mean, look at when they first introduced MIG welding. Like everybody was I don't trust that. You got a little tiny wire coming out of there. No, I'm going to use this stick. Been using this stick for 20 years. It's never let me down. And now you got like this little wire coming out of a gun. You got a gas mix in there. Like we're not doing that.
Yeah. Well, it's like now that, but like so many of us. So I think Nate and I touched on.
So it's kind of funny that he says that, because the history of welding in general is like that. So even back when acetylene welding or gas welding was popular, electric arc welding, which was stick welding, came along. Let me think about that. Early 1800s, I would say, would be the first time that I think it was Humphrey Davy? Sir Humphrey Davy was the first one to actually weld two pieces together. I think that unless I'm mixing everything up, about 1801. And it got further developed, and then by 1887, a couple of Russians got together, and then there was another guy over here in the United States that also stuck two pieces together with a stick weld. And at that time, gas welding, acetylene welding was also relatively new. Now, when I say relatively new, I think they had been doing it for about 40 years at that point. And everybody came up and said, hey, look, we can weld with electricity. Well, at the time in the 1880s, electric arc welding, or electricity in general, was about as unknown as space is to us now. They knew enough to be dangerous with it. So when acetylene welding was around, Lincoln Electric and another company that was in Europe was trying to push arc welding into the industry. Well, not a lot of people bought it. They were like, well, we've been doing this gas welding thing for 40 years and it's worked just fine. So we gas welded, or acetylene welded, pretty much everything up until about the end of World War II. So a lot of the pipelines that have been built pre-World War II are acetylene welded together. And the only reason why I know that is because there is many times where we have had a smart pig go through a line and it detects an anomaly in the pipe. We dig it up, come to find out it's an acetylene weld. And the reason why we knew it was an acetylene weld is because when they did acetylene welding back in the day, they didn't really have X-ray for steel really figured out yet. It was mostly visual inspection stuff, so they couldn't see the inside of the pipe. And they would just hump it up until they thought it was good. And so these acetylene welds are huge. And we know better now that that's actually worse. But point being is that these acetylene welds were considered kind of cream of the crop, the way to do things, up until about World War II, where things started to shift around. And, the 1940s, we saw a huge boom in electric arc welding. And acetylene welding started going to the wayside. And honestly, you could acetylene weld, you could gas weld. People were still taught how to gas weld up until like the 1990s. And even further on, there were still gas companies that still used acetylene welding in their procedures. There weren't a lot of people that did it, but it was still around. Now, with the way things are set, acetylene welding is no longer allowed at least on pipe and on major structures. It's still a practice that is used in some cases, but it's very seldom, and it's also very hard to find somebody that is really good at it. I'm not really good at it. I can stick two pieces together with an acetylene weld, but I'm not, I wouldn't have enough confidence to do a critical weld with it. So, but that's kind of what they're talking about. This whole laser thing is now new, and everybody's kind of pushing it to the wayside, like, we've been using this arc welding for years. Or when MIG welding came around in about the 50s, not the 50s, when was it? What was it, like the 30s or 40s, something around that time, MIG welding came around. And at the time, MIG welding was actually used to join aluminum together because aluminum was becoming more prevalent, and it was really difficult to weld with stick welding. Matter of fact, it was damn near impossible. Now, we have stick welding electrodes for aluminum now that are actually really good. It's still a pain in the ass, but they're still good enough. And I still say to this day, MIG welding is just a lot easier for aluminum. But at the time, people were like, no, why would I do that? This has been working just fine. I'm not going to go to new technology. And the human race is notorious for being scared of change. So that's kind of what they're going into here. Let's see what else they say
on this in the video, right? And we had that old guy come into the shop that I was training people on. He's like, this is great. It's like MIG welding, and nobody believed in it. And it was like really cool for me to see like this 70-year-old guy come in, because like usually they're crotchety, they don't want anything to do with new stuff, and he's like jazzed about it and made that parallel. And I was like, man, this is so cool to hear that. And, you know, I think a lot of people get really excited about handheld laser welding, and I walk into a lot of shops and people are like, oh, we're going to replace all of our welders with handheld laser. I'm like, whoa, 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 whoa. Like, pump the brakes. That's not the case. It is another tool to add to your toolbox. You will figure out where and how to use it with your existing technology. It will make you faster. It will make you more efficient. It will make higher quality welds in some situations. In some situations, you don't want to use it at all. But in others, if you can find out how to use the two together, it'll be more powerful than you could have ever imagined. Like, I'll tell you, some of the things that we did at SpaceX, like I was in the lab one day and I was like, okay, let's lay down a laser root. So like, you know, you think about making a groove weld. And I think this is where handheld laser weld came into ASME Section 9 is like, well, hey, why don't we just do a deeper penetration root pass with a laser and then cap it afterwards and we reduce our bevel size. So, you know, I was like, well, dude, what happens if we do this to a fillet weld? Right? So let's make this high power fillet weld. And so we've got this 50 thousandths root pass fillet weld. And, you know, maybe we penetrated, you know, 120 thousandths into that joint. And now let's go cap it with a MIG weld and put like a 1/4 inch MIG weld on top of that. We might have a 1/4 inch MIG weld, but now we've got like maybe a 3/8 inch throat on that 1/4 inch MIG weld. It was the strongest weld I have ever seen in my life when we went and broke it. It was wild. And what really excites me is once I see people understand what handheld laser welding is capable of, dude, welders are some of the most creative people on the planet, right? and seeing what other people do after they learn how to use the technology, for me, is so fun.
It was designed to do this. Let's see what it can really do.
Mm-hmm.
Oh yeah, they'll test the shit out of it.
Yeah.
Now, have you like you were talking about mixing processes? Have you done any like laser hybrid welding where I just read an article the other day about, I guess they run a laser in front of like a MIG application or a TIG application, so you kind of get that keyhole effect. You kind of preheat the part and everything. You get much better, faster welds because the laser's preheating and opening everything up ahead of you. Have you done anything like that?
I haven't done any hybrid per se. I've done a lot of like hot wire work, which is similar, just no arc. But yeah, you're totally right. There's a number of applications where people are doing hybrid. I think especially in Europe, in the shipbuilding industry, they use a lot of automated laser. And the benefit there is, you know, you've got your MIG weld, you've got all that filler material, you've got a much bigger melt pool, and you can fill larger gaps, right? That's one of the traditional disadvantages of high power lasers is traditionally, if you're trying to make a laser weld, you have to have less than a 5 thousandths root gap or you're going to be underfilled. If you're lucky. If you're unlucky, you shoot right through the joint. A handheld laser, I think, is a little bit more forgiving because you're adding that wire. I typically tell people you can close, you know, 1/2 to 2/3 of your filler wire diameter. But every once in a while, someone asks me, like, what if someone made a hybrid MIG handheld laser? Like, I don't know, what if? Right? Someone will do it eventually. I don't know if it's actually beneficial. But yeah, there's all kinds of crazy stuff.
It's kind of cumbersome.
Yeah, it's pretty nuts to see how like technology is changing in the welding industry, like day by day. I mean, I thought it was the coolest thing when they came out with like pulse welding and, you know, STT and RMD and all that stuff and pulse on pulse. I was like, man, this is like really cool technology. Now there's a whole new process coming about, you know, laser welding. It's a completely different, you know, and I would imagine they've had the technology probably 60, 70 years if it's like anything else. But I mean, they've done like plasma arc welding. I mean, that's not too far.
Thanks, I'll have to look them up.
Lasers essentially mimicking.
I want to get...
Yeah, and you know, I think the world...
I'm kind of doing a lot of research on these laser welders because I was kind of in the same boat in the beginning where I thought they were a gimmick. And the more I read into them, the more I realize that it's actually a useful tool. And it's also not something that's going to take over the other processes that we have. It's just a useful tool. So they were just talking about, you know, maybe doing a laser weld root and then capping the rest. It's kind of funny they say that because at least in the pipe industry, we're kind of looking to transition slowly into a combo weld. And a combo weld is a TIG root with a stick weld fill and cap. The reason why they do the TIG weld is it's a lot cleaner. At least in the petroleum, oils, and natural gases, when we do a root pass with stick, you also get the slag on the backside. Now that slag gets cleaned out when the if we do a poly pig that goes through the line to clean the line out, it'll knock that slag out. Now the thing is that that slag will go down the line and get stuck in the strainer, which the strainer or the filter that's its job, is to filter out all the crap. And the TIG weld is a hell of a lot cleaner. It's not as fast, but it is a lot cleaner, and it is also less brittle. The thing is about doing an open route with stick welding is that you're using usually 60-10, 70-10, 80-10, and these 10 series rods they're really strong, but they're relatively kind of brittle when it comes to expansion and contraction. Now you can mitigate that by doing 70-18 hot pass, fill, and cap. 70-18 is much better against metal fatigue than what the 10 series rods are, or 80-18 or whatever you're going to use. But at the same time, we're still stick welding. It's still a lot of slag. It's still dirty, more or less. They're still really clean welds. I mean, for example, well, what I should say is one of the reasons why we use 10 series rods on pipeline that's underground is that we're not worried about expansion and contraction so much, because the ground temperature is typically stable. Up where I am, the average temperature underground is between 50 and 62 degrees. That's pretty stable. So we're not going to worry about expansion and contraction so much. The pipe's just going to stay how it is. But above ground stuff, that's a different story. Now, for years, we have done 60-10, 70-10 welds, or 60-10, 80-10, or whatever combination thereof, and they've held up just fine. We haven't had an issue, but we can make these a little better. So that's the idea of the TIG route. Now, the laser welding route, that adds another thing to it. The one thing about a laser weld route is I'd be willing to bet, A, you don't have to take as much space, if any. You leave a knife edge on that bevel instead of grinding a land on it, butt it together. You turn your kilowatts up a little bit, pick a wire speed, and then go. Now, the weld's very small, but you get 100% penetration. It's a super clean weld. The heat affected zone is very small, and then you cap it with another process, whether it's stick weld, MIG weld, flux core, whatever floats your boat. So I really am curious to see what happens in the future. Spider on the windshield. Yeah, I got a lot of
industrial fiber lasers. It's maybe I would say high power fiber laser welding is probably 25, 30 years old. Of course, there have been lasers around before that, just not with high enough power to do like big industrial things. Now, I think like the really interesting thing here, like building off what you said, humans have been arc welding since the late 1800s, right? So say like 130, maybe 40 years if we're being generous, but well over a century, humans have been arc welding, and we're still learning, and we're still...
Please tell me that shut up on the camera. That guy's muffler, a catalytic converter, was glowing red. Oh my God, he's gonna start fire.
Affecting the technology. In the world of handheld laser welding, for comparison, it's been around in China probably for the past 7 or 8 years, and the first machines were gaining popularity or being introduced in the United States, late 2020, early 2021. So we're really only 5 years into handheld laser welding. And as we discussed before, nobody really knows even the basic process fundamentals of handheld laser welding. I have no idea where it's going to go in the next 10 or 15 years. And that's what excites me. Like, I love the challenge. I love doing new things. Like, if I did the same thing every single day, I think I'd just give up on life, man. Like, I love the challenge. I love doing new things and finding things out. Like, then I went to the eye doctor a couple weeks ago for my yearly exam, and I think that morning I had been trying to solve some crazy problem in the lab. And I went to the eye doctor, and I'm sitting there at the eye doctor, and they're running through all their lenses and stuff, and I'm like, man, F you. Your job's the same thing every single day, and you go to work and you do the thing, and it's maybe you're not doing anything crazy, but it's easy, and you get paid and you go home. And then I'm go back home, and I'm tearing my hair out. But it's I really enjoy that kind of challenge. sometimes it sucks, but like, you don't learn without struggling. You don't learn how to make good welds or good things without making some bad ones along the way. And I'd be so bored if I was an eye doctor.
Oh, for sure.
But hopefully, with any luck, we can make life easier for everybody else who's trying to learn how to get it.
Definitely. Now, what are some of the disadvantages when it comes to, because you said it's not like the silver bullet, you're not going to use it for every application. It's not going to replace every welder in the shop. Like, what is,
man, my gas mileage is suffering going up this mountain
when it comes to laser welding?
Yeah. So I think number one is finding the right material to use it on. So it really excels with gauge thickness materials. Once you move into plate, you can always weld thicker material. The laser doesn't care how thick your material is, but as your material gets thicker, your weld size also often has to go up. So yeah. I think it really excels at gauge size, like 10 gauge. I've got a number of customers that weld 8 gauge. So let's say like 8 gauge and thinner. It really excels at.
I've never heard anybody say
like 4 and above, even sometimes like 3/16. Depending on the fillet size you're looking for, it becomes more difficult. You have to do a multi-pass weld. And at that point, I think I just switch over to MIG. The other thing is filling gaps. So if you've got a gap, let's say you're running 1/16 inch wire, figure you can close a 30 thousandths gap, 40 thousandths if we're being generous. So if you've got a gap bigger than say 30 thousandths, it's going to be pretty tough with laser to do it in a single shot and to do it well. Joint access can sometimes be a struggle. The torch is fairly bulky. I think they'll
looks a little
probably right. They'll probably someone come to me
made this
over
drive
a year ago, and they were making these little.
I've made this drive many times.
Experiment.
At least this part of it, and I've always wanted to know how high this mountain actually is. I go up here a lot, but I've never actually checked the altitude. So we'll see. Right now we're at 1,100 feet.
And I was like, that's not going to happen. You can't fit the torch in there. So torch access is important. One thing I see, how come we're always seeing like straight welds with handheld laser videos and nobody's doing any complex geometries or like radii or anything?
Or 1,200
I think that's
feet.
more of a misconception, just because not that many people are doing things out there. You can totally weld tight corners. Like I said, down to maybe 3/8 of an inch. 1/4 inch is really pushing it. Like I've done that a couple times for people, but it's not fun. 3/8 of an inch is doable. But I think those are like the big 3 limiting factors. Right? Your
1,400 feet.
Your gap size, your material thickness, and the torch access.
You can do pipe and tube now, because I remember, I think somebody was talking to one of the guys who were like
1,500 feet
at FabTech probably 1 or 2 years ago, and they said that was like one of the limitations, because they wanted to buy it for roll cage applications. And they're like, oh yeah, it's just because the joint geometry and the configuration, like it'd be very difficult to do that, because I guess both prongs have to touch base metal as you're going around.
1,600 feet.
Yeah, so I think it's possible. I think coped tube joints are pretty easy. Doing like a groove weld, like a butt weld between 2 pipes, it's doable. It's a little trickier. That's where I think the torch access comes more into play than anything else.
At the top of this.
But yeah, you can totally do it. I did a job for someone, it's like a month and a half, 2 months ago, where they wanted to know if they could do this.
What did I end up hitting?
This steam power plant header manifold with like all these big stubs to ASME code, and it had like a 3/8 inch bevel and needed a 3/8 inch fillet on the outside of the bevel, and someone came to me like, you think you can do this? And I was like, that seems crazy, man, but why not? Because I've done similar geometries in thinner material for like vacuum chambers and stuff for people, and we had started using the TIG rod feeder, and I was like, well shoot, man, we'll throw some 3/32 or some 1/8 inch TIG rod in there, and we'll see how many passes it takes to fill it up. And we did it. It was pretty cool. Did it meet code requirements? Yeah, actually it did. Was it perfect? No, it's like the first time anyone in the world had ever done anything like that, as far as I know of. So I think like the areas and the applications that you can use handheld laser in will continue to grow the more people try to play with it.
Okay, because I know it's like some of the advantages are like you got less heat input, so you don't have to worry about material warpage and all that stuff. I guess allegedly you can weld underwater on wet parts, whereas like that's highly frowned upon with arc welding processes because of
I
hydrogen.
wouldn't call it.
Back
I
down to
wouldn't call it a
1,500
party trick, man. Makes for a great video, right?
Okay, so you wouldn't recommend welding over top of or underneath water with a laser?
I would not.
Okay, so yeah, because like I would imagine you'd be ionizing the water and converting it back into hydrogen.
Yeah.
Yeah, for like carbon steel, yeah, there's lots of hydrogen. It's probably not great. I imagine if you cut that thing open, even with like a stainless steel, you know, who knows? I don't want to speak out of turn. I've never cross-sectioned a stainless steel handheld laser weld that I made underwater. Maybe I should. Yeah, you see those videos though.
So they're talking about some of those videos where you see them welding underwater, and I always cringe when I see them because one of the enemies to welding is hydrogen. Hydrogen getting into a weld can cause cracking very severely. So a lot of mitigations have been made in these filler metals to get rid of the hydrogen. So it's a 7018. The 7018 is considered a low hydrogen rod. That's why it's got to be kept in a rod oven to keep the moisture out, so it doesn't have any water in it to convert to break apart, ionize it, and make hydrogen and infuse hydrogen into the weld. So I can see why that would be a problem. Right.
Like, just because it can be done doesn't mean it's a good idea. I think, you know, we did a video with Weld.com earlier this year, and it was like, well, what materials can we weld together? And they're like, well, let's weld all this crazy garbage together. And I was like, look, man, we can weld it, but it doesn't mean that it's metallurgically compatible. So yeah, there's always, can you make it stick together? Yes. Is it good? Debatable.
So dissimilar metals is still not
dissimilar metals dissimilar metals is doable. Yeah. So like in my life, I've done a lot of dissimilar metal welding with lasers, primarily automated lasers. So lots of times it's either copper and stainless steel or copper and carbon steel.
So we're at
there's a lot of weird metallurgical things that can go on there. Again, I'll go back to that word of dilution. It depends on how much of one material gets mixed into the other. It's very doable. It's possible with handheld laser welding. Like the two, as long as your dilution is correct, the two are very compatible. Where it gets goofy is like, well, hey, I want to weld aluminum to stainless steel. It's like, well, okay, that's not really possible. You're going to get brittle intermetallics. Yes, you might be able to fuse it together. It's going to fracture almost instantly after you weld it. And so I think it's less a question of process capability and more a question of metallurgical capability. But yeah, copper and stainless, copper and carbon steel are very, very common applications for people to do dissimilar metal welding. We did some copper to aluminum when I was doing the videos with Weld.com. We're using 6061 and like 6061
to drive through the mountain road right now.
Okay, if we took some 2219, which is actually alloyed with copper, I think it would be a different story. You could probably weld copper to aluminum, no problem there.
I definitely don't have time to do that.
That's where it comes down to metallurgical capability and not necessarily process capability.
You got to try galvanized
nice thing is I'm literally halfway there.
So that's the friendliest party trick.
I was going to throw their name out there. Yeah, the cold metal transfer. I think they designed that specifically for the Mercedes-Benz bumpers.
Yep. Yeah, that's like that big party trick.
I appreciate it. I got a long time. I got a long way to go yet too.
One specific
application.
I appreciate you being here though.
No, it's pretty neat. I mean, like just the whole technology like coming about. I mean, it's really cool to see a new welding process being, because I mean you're probably a little bit younger than I am, maybe about the same age. It's like seeing a new welding process being introduced in our lifetime. You know, because there was a lot of people that, I mean, all they ever had was stick, MIG, and then like they introduced TIG. And
so when I got this new job, first thing I said to myself was, if I'm going to be traveling, I will not survive in the truck that I had. I used to have a 2019 Ford Ranger, and I loved that truck. I was not looking to get rid of it at all. But when this job came up and they said I was going to be in the truck a lot, basically working out of my truck, first thing I thought of was, I'm not going to make it. I bought that Ford Ranger brand new in 2019 because at the time I was working as a welder for the natural gas company, and I had a work truck that I took to and from work and everywhere. And the only reason why I drove my truck was for, you know, little errands around the house and up in the mountains, actually here, hunting. And it was good enough for that. I remember taking it to Tennessee, a 12-hour ride, following my wife and kids in the other car that we have. And the reason why I was going down there was my CWI test, but we decided to make a little vacation out of it. And I remember sitting in that seat just in agony because I was so uncomfortable. I am about 6'4", and in that little Ford Ranger, the seat would not go back far enough, so my legs were up and my thighs weren't touching the seat. And, you know, for short rides, hour, 2 hours, I'm okay. But then when anything more than that, it hurt. I mean, it was not fun. So first thing I thought of was I need to get a truck that I can drive in. I may need to get a full-size truck, as much as I didn't really want to. And then when I was talking to the company I'm working for now, they had told me that because I'm using the truck for work, I get reimbursed for, you know, maintenance, wear and tear, mileage, and all that stuff. And it's a sizable amount. It basically covers my truck. So yeah, my knees were killing me. Like, my knees were killing me, my hips were killing me. I'm in good shape relatively, but I have had injuries to where it makes things, especially my left leg, much more unbearable. And, you know, I've been worse, but it was not comfortable. So I got rid of that truck and I got this. This is a 2024 Chevy Colorado Trail Boss. And I got it for, well, I mean, I thought it was a really good deal, but it was basically MSRP for the thing, but I'm not complaining about it. And the biggest reason why I got it is because me being 6'4" and 255, 260 pounds, this seat fits me so much better. I have more adjustment to it. I can adjust the rake of the seat because it's a power seat, and I can adjust the length. Like, I can even go back. I'm going to go back a little bit, and it stretches my legs out. It feels so much better. I don't have any of that special stuff. I don't have radar, cruise control, lane keep as well. Actually, I do have lane keep assist, but I leave it off. But I don't have any of those electronic nannies to watch you. So this is a work truck with an off-road, with a 2-inch suspension lift from the factory, basically, and some bigger tires. But as a road trip car, this is miles better than what I had. I almost bought a new Ford Ranger with the twin turbo V6, and it was a very potent little engine. It was a lot of fun to drive, but I had the same problem. The same problem is I didn't fit as well as I should have. So that's why I ended up with this. But I can sit in this seat, and I just did it last week where I did another 5-hour drive where I had to go up to Connecticut and back in a day. Well, in 2 days. I went the night before, slept at a hotel, did my training I needed to do, and then drove back. And it really wasn't that bad. A little achy in some spots. You know, I took like one break, but all in all, it was pretty good. And this truck is a fantastic road trip truck, which I'm surprised because I read a lot of reviews, and one thing they didn't like was how stiff the suspension is. I don't feel it. I mean, it is a little stiff, but at the same time, this rides smoother than my Ranger did, in my opinion. And it's got plenty of power to get around. And the miles per gallon's better on this truck than it was my Ranger, which is surprising. It wasn't supposed to be, but so far it's been good. We'll get back to this.
And, then they retired from the industry. Now there's like all these different welding processes out there that people are getting into, and all the different, problems we can solve and challenges we can overcome with just switching the process, or, stepping back and taking a different look at it, and, seeing what's actually possible with some of this stuff.
Yeah. What's really interesting is, like, you see all this, like, new technology, and I met this guy, it's probably like 12 years ago or so, who's like a very skilled and intelligent inventor who's got like probably over 100 patents. And the thing that he told me is, he's like, look, nothing is new. Creativity is recombinant innovation with a twist. And his meaning with that was, everybody who's inventing something new, they're just taking things that already exist and like smashing them together in a way that someone hasn't before. And so like it's like interesting for me. You're like, yeah, this new handheld laser welding technology, and like for me, I'm like, I don't know, it's lasers. I've been doing lasers forever. It's just like another thing, right? But it's like it's that recombinant innovation with a twist. It's just someone was like, hey, why don't we put this in someone's hand? And I think it's the same thing with like all these like pulse mig and short circuit and all these other like fancy things that are coming out. It's just people smashing existing things together in different ways. And you know, shoot, man, like I said, who knows where handheld laser welding will be in 10 years? Who knows where arc welding will be in 10 years?
Sure.
I know.
Well, that's like the STT, the patent on STT, surface tension transfer. It came out in like 1986.
Yeah.
And it never really caught on until 2020. You know, or 20.
Hell, I was doing STT
2018, where more and more people are
almost 20 years ago.
Because we're like, no, we're just gonna run this short circuit in here and wish for the best. And it's like, there's a better way.
Yeah, STT
like,
like 15, 20 years ago.
Adopt new technology.
Yeah, I think the same thing has happened and is still happening with handheld laser too. Is I remember 10 years ago, people were so excited about Fronius CMT, and all these like big companies were buying CMT systems, like big, like $40,000-$50,000 for a CMT welder, and the welders are excited about it for a day or two, and then it just sits and collects dust because like nobody knows what to do with it. And I think it's been the same thing for a lot of early adopters of handheld laser welding. Like you see these people who are curious or maybe see the potential and they buy one and they're like, what do I do with this now? And it just sits and collects dust.
I've been a welder for about,
eventually people figured out
I'll explain. If you want to know my full story of how I've gotten where I am, earlier in this live I explained it, but to give you a better idea, I was a welder for a contractor doing pipeline work for oil and gas for about 7 years for them. I went to a natural gas company for another 7 years, and then I got my CWI license and my CWE certificate. And for the past probably 2 years, I've been in between inspecting and instructing. And now with the company that I'm working with now, and the reason why I'm traveling is because I am a company welding inspector for a pipeline company. And so I inspect welds. Now this channel is for learning how to weld, and originally this channel was for learning to weld in your own home. So, inexpensive welding machines, projects that you can do yourself at home, stuff like that, tricks of the trade, you name it. But with me traveling so much now, and this is very recent, I'm probably not going to be able to do as much of that as I intended to originally. So it's going to be a little bit less of actual welding and more probably career stuff, or maybe welding deals that I can find, or we'll see how it goes. Talking to a couple friends talking them into doing a podcast with me. So we're also going to see how that goes as well. I started a podcast back in January, and I did like one episode and I didn't have time to keep up with it. So now with me traveling as much, I think I will be able to keep up with it, because I'll be able to talk while I'm driving, number one, and number two, when I'm sitting in the hotel room, maybe on a rain day, or time that I have off, if I have any, I'll be able to do a podcast, kind of like a call-in podcast for a bunch of people. So we'll see how it goes. But I've been a welder for years. I still weld at home. The projects that I was doing on my channel, I'm still doing them. They're just going to take a lot longer now, because instead of having 4 nights a week, I have one if I'm lucky. So
it's this controlled short circuit. Now it's becoming more popular again. I think the same thing will happen with handheld laser as knowledge becomes more available and people figure out how to use it.
I appreciate that.
Dusting off their machines and putting them back into service.
I get a lot of people to school. They're like, "Have you ever done laser welding?" No, haven't tried it yet. And I had one guy. He specifically took my class because he builds gates and handrails, and he's like, "Well, I'm saving up right now for a laser welder, but I think if I learn this MIG and TIG class that you're doing, I'll have a better understanding of the laser once I get it." I'm like, possibly. I said, but I don't want to misinform you. I said, it's probably apples and oranges as far as like how the settings go, the technique, the setup, all the stuff that you're going to have to figure out.
The fundamentals are still there.
Make a TIG if that's what you want to do. But a lot of that info, some of it will translate over into laser, I'm sure, because it's another welding process. But a lot of the stuff as far as like settings and gas composition and the consumables, like that's going to be completely different.
Yeah. You know what's interesting is like, for me, I deal with a whole lot of different customers, and it ranges from like small mom and pop job shops all the way up to large aerospace or Fortune 500 companies, and trying to help them understand how to use handheld laser welding. But for me, one of the things that I'm always thinking about is like, how do we make this knowledge accessible to the average person? And I think for the most part, like handheld lasers are not necessarily accessible to the average person right now, but I think a key part of making
they're expensive.
a normal thing is making that knowledge accessible. And so we've been toying with the idea, and I think we'll do this later this year, of hosting classes here in Seattle, and probably having, I don't know how many arc welding systems you have when we teach your classes, but we'll probably have somewhere on the order of 6 lasers, and do a 2 or 3 day long class where people can come and learn the basics at a much lower price point than if we were to come out one-on-one and do it at people's facilities. So I'm actually really excited about that.
Let me know, because I mean, like 5 is like ideal. That's I've got 5 set up at my school.
Oh no, I'll never get bored doing this.
The week-long comprehensive class.
Absolutely not. A matter of fact, I've spent a lot of time past 2 years or so kind of soul searching,
5 to 6 people is pretty optimal.
When I started welding,
And then, like
pause
you said,
this
you can
again.
make it- It's a lot more affordable for.
When I started welding, I thought that's all I was going to do. And then a couple years in, I did my first job where I had a CWI watching me 100% of the time. And I had never experienced it up to that point. And he was a really nice guy. And I started talking to him about what he does, because I didn't have a clue. I didn't know. All I knew is that he was watching me weld to make sure I was doing it right. And come to find out, inspection's not like that. As an inspector, I'm not there to watch a welder to make sure he's doing his job right. And for the most part, welders know what they're doing. What I'm there to is to ensure quality. So it's not just welding. I am looking at their welds to make sure they're doing it right, but at the same time, it's not for me to judge if they're doing it wrong and how to fix it. It's just me verifying that he's following the procedure in hand. So him talking to me and explaining how CWI works, I decided right in that moment, well, not really right in that moment, he talked to me a little bit, we got done the job, and then he invited me, after the job, invited me over to his camper to talk for a little bit. So inspectors cannot engage with the welders they're watching as far as like friendly talk like that until the job's over. Once the job's over, it is what it is. So he invited me over, and come to find out, he didn't own a house. He had a piece of property in his home state. He had a P.O. box just for tax reasons and for a place for his mail to go. And he traveled 9 months out of the year. Well, he worked 9 months out of the year. He traveled 100% of the time, but he worked 9 months out of the year. It was his retirement gig. He would come out, do some welding jobs, watch some of the pipeline work, do all the paperwork, do everything that he needs to do, and he would just live in his camper. Now, his camper was not just a little camper. It was something like a 52-foot, I think. It was a triple axle, and he towed it with an F450, loaded out F450. And this was such a massive freaking camper that it had its own one-car garage in the back. Like, it wasn't like a typical toy hauler where you fold up the beds or something and drive in a motorcycle. Like, no, you could fit a decent small car in the back. It was awesome. But he didn't have a house. That was it. He sold everything he had after he retired, sold all his stuff, and bought this camper and truck and started doing this for his gig. And I remember thinking, when I was talking to him and I was sitting around the fire talking about all this stuff, I said, that's what I want to do. Maybe not quite to that extent, but that's what I want to do. And that was kind of my goal from that point on. And that was back in, I don't know, 2012, maybe? So that was my goal. I just set my head that. That's what I wanted to do. And I took the CWI test in 2021, passed it, and then I was searching for CWI work ever since, and landed me here. This company that I'm working with now is a company that I actually contracted for way back, and most of the people that I worked with or worked under or did their jobs, they're still at this company. I still know them. And I just started this job, by the way. This is my first actual project that I'm going to, but I happen to know a couple of the guys that are going there, so it's going to be pretty familiar. But yeah, that's kind of my spiel.
Them to come to me than it is for me to pack up all my stuff and go out and travel for a day.
Yep,
It's a lot more affordable that way.
and if you've got 5 or 6 people sharing my hourly rate, it's a lot better than one.
Yeah, exactly.
Right?
Yeah, I can imagine, because you've got a niche market there. Yeah. So like you train customers and stuff like that, I guess, that are looking for laser technology, not just like an average individual that wants to roll it off the street and learn laser weld, but like you do consulting for like bigger companies to come in. You know, they invested in a laser welder. They can come to you for training, and like you said, you're kind of agnostic amongst brands. So I would imagine you have a couple different manufacturers, machines at your facility.
Expansion joints are a little bumpy on this road.
Yeah, so typically, we work with people. A lot of people have already bought a laser. Some people are thinking about buying a laser. And so we'll kind of help people along their journey. We'll do lab work, help people prove out that it's a good idea. And then a lot of times, like the vast majority of our customers will actually go visit their facility and teach them how to use their equipment and, do a site walkthrough and help them understand, hey,
yeah, I'll be traveling quite a bit.
Here's a low-hanging fruit for hand laser welding. Here's where you could go in the future.
I've got 2 projects. This one I'm only going up here to help them out. But this is not my project. This is,
but what's been really fun lately is kind of as
they just need a little bit of extra help. So they had asked me if I wanted to go up for, I don't know, a week or 2 and do this with them and kind of get some, not throwing me to the wolves, but the best way I learn is to just jump in and figure it out. I've always been like that, and they know that. The company I work for, they know it. So they asked me if this is something I wanted to do. I said, yeah, send me. And well, I didn't really have a choice, to be honest with you. It was just kind of how it was. But I'm not upset about it. It gives me an opportunity to really be thrown out and just get my hands on it and learn exactly what I need to do for my position. I know how to be an inspector. I know how to do all that stuff. The thing is with being with a company is learning their processes. No, I'm not going to Texas. I'm nowhere near Texas. I'm going to Ohio.
People always told me before I started doing consulting, like, oh, it's feast and famine. Sometimes there's a lot, sometimes there's nothing. And so the question is like, what do you do in the background to sustain your business? And, one of the ideas early on was like, oh, let's make like a consortium research group of a bunch of large companies that want to solve these problems together. But the fact of the matter is, like, large companies don't want to shoot each other. They all want their secrets. And so I think like this school is an easy way to do it in the background. Like, and don't get me wrong, I got before the podcast started. Like, people want handheld laser welding knowledge so bad that the institute has grown faster than I ever expected. And so things are great. We're constantly busy, but I love educating people. I like seeing people understand what's going on. And that,
I can't believe I'm still wide awake.
Next direction for us.
Usually by this time I'm starting to get a little tired. I was thinking about stopping at about the hour-and-a-half mark and getting some sleep at a hotel, but I don't know. I might just drive all the way through. We'll see what happens.
Podcast full time, doing consulting and some testing, and it wasn't a steady flow of work. And then when I opened up the school,
In all honesty, I get there, it's not going to be that bad.
Now that I have the school and the testing center and the consulting, it's like I've got 3 non-competing sources of revenue.
I should probably stop.
Business of training, education, and certification.
Well, now that I think about it,
fall under the same umbrella because it's all welding related. So one week I'm teaching a group of students. One week, testing a group of people. The next group, the next week I'm like consulting on projects, building procedures and stuff. So it sucks when all 3
it's not going to much matter.
into the same week. that gets a bit hectic. But it doesn't always happen like that. So it's always good, especially if you enjoy teaching
Yeah, we'll see. I don't know.
Open up a small section of the school, do short-term classes and stuff like that, because welding is, or laser welding rather, it's going to get more and more popular as we go. I mean, I just and they're already using it in aerospace. It's not going to be automotive. They're probably using it in automotive. It's not going to be long before the pipeline adopts, some portion of it. Structural steel starts to adopt. Like I said, there's a guy out there that he came to my
Making
school,
really good time.
Stairs handrails. Just because it looks so simplistic to do.
Yeah.
So I mean, I think that's going to catch a lot of people's eyes too.
Thank you, Ray.
I mean, we'll see what happens. I'll get a feel for it.
Out of here, tell people where they can.
I hit
you,
about
be it on YouTube, Instagram, websites, all that stuff. If they want
we'll
to
see.
take classes, or if they want to just learn more.
Maybe I'll drive through. Maybe
I'll.
I
You guys do at the Handheld Laser Welding Institute.
Yeah, so our website's
the thing about this truck, it's actually pretty comfortable to just sit here
It's got
and
most of our
drive, and I'm
information,
not
services, links to all of our YouTube videos and podcasts like this one. Great information about getting started, and then also on Instagram, the Handheld Laser Institute.
Awesome, man. It's been an absolute pleasure chatting with you. I look forward to seeing you at FabTech in Chicago and stop by and playing with the laser.
I'm past the halfway
point
point now.
Some more of the theory and applications.
Yeah, no, I'm at the
Absolutely,
halfway
man.
point right now.
Looking forward to it.
Likewise. All right, ladies and gents, I hope you all enjoyed the show.
Going
If you're
uphill
finding these
again, aren't
episodes
I?
beneficial to your welding journey, please leave me a review on Spotify.
Oh, yeah, we're going up.
And consider sharing the episodes with a friend. You can also stream episodes directly from my website, arcjunkies.com, and feel free to hit me up with any questions, comments, or concerns by sending an email to show@arcjunkies.com. I hope you all have a great rest of your week. Stay safe out there, and until next time, make every weld better than your last.
Going up and up and up into the Appalachians. What's this one? Battery powered welders. Dead. Oh, this. I want to get my hands on a battery powered welder so bad. Oh wow, pretty good on time. Starting to lose a little bit of cell signal though.